The next speaker of the session is self-announced. It's me. This is our attempt to accommodate for the changes in the schedule. Okay, I decided that I could have approached it differently, but I decided that I'll probably just speak from the perspective of Bob's former student, and I would like to talk about the time that I spent as a PhD student in Bob's group. So, but the reason for this decision is the fact that my favorite project still remains the one that I performed at the end of my PhD studies, which I like to call unusual manifestation of local field effects. So I would like to acknowledge my other mentors who also have been guiding me through this project at different stages of it. It has multiple branches to it, and we collaborated with Professor John Sipe and Professor Peter Miloni, who is here. Thank you very much for your kind guidance and patience in teaching me. Also, Dr. Hiduk Shin, who is here, was another student working on some experiments in this project. So I would like to acknowledge these people. And this photo I like to call mentors, because here I am back 10 years ago with Professor Boyd, Professor Miloni, and Professor Sipe. I really like this photo because this completes the supervisors for the project associated with local field effects and nanostructuring. So let me just speak simplistically about local field effects first, and then where did it lead us at some point. So first of all, if we imagine a material medium as a collection of dipoles, let's assume just a three-dimensional case, but here is a projection, two-dimensional. And this set of dipoles gets illuminated by the external optical field. The field X entering Maxwell's equations is the average field in the medium, E, shown with blue arrow here. But the local field is the field that acts on individual dipole in the medium, and it is neither the external field nor the average field. It is different. And in fact, it is the local field that drives the atomic transitions, and as a result, it is the local field which is responsible for the optical response of the medium in both linear and nonlinear optical regimes. So the simplest model for accounting for these differences in the local field and the average field is Lorentz model of local field, relating local field to the average field in the medium and the polarization induced in the medium. Alternatively, this relationship can be represented in terms of the local field correction factor that is related to the dielectric permittivity of the medium, according to this expression in the pink box. So this is the definition of Lorentz local field correction factor. So the focus, we extended to the nonlinear optical regime, and the focus here is microscopic cascaded nonlinearity, which I was able to uncover when simply solving basic equations, extending them to higher than the lowest order nonlinearity existing in the medium. So let me just use an example of non-centrosymmetric medium in order to demonstrate what does one mean by microscopic cascading, the names that we had to introduce in order to discriminate, to differentiate it from the macroscopic cascading effect. So in a non-symmetric medium, the polarization, non-centrosymmetric medium, the polarization can be represented as the sum of the linear term and the second order nonlinear term and the third order nonlinear term represented by the corresponding susceptibilities, chi1, chi2, and chi3. So the first contribution that could exist to the phenomena of third harmonic generations that I picked just as an example for demonstrating this. The first is the most obvious one that comes directly from chi3. And it is arising from interaction of three photons with the medium by means of chi3 and the appearance of the photon at the tripled frequency, 3 omega. That's the most obvious one. Second contribution is also well known. It is a cascaded contribution of chi2 effects to chi3 to Chi3, like effects, and it requires a multi-step Chi2, such as, for example, second harmonic generation by means of the first Chi2 process, and some frequency generation by means of the second Chi2 process. And at the end, we get the same, 3 omega photon. So this is cascaded contribution, but this is a well-known effect, and it has been used because it has a higher probability of occurrence. It has a much higher efficiency compared to the direct Chi3 effect. For that reason, it has been popularly exploited in crystals, in nonlinear optical crystals. So this is macroscopic cascaded contribution, which is well known in order to differentiate it from the other cascaded contribution. So, but the cascading in the sense we mean here within this project is a different kind of cascading. And below is my attempt to explain it physically. How does it occur? So let's now take a look at the same medium that has both Chi2 and Chi3 present. But let's now concentrate on one specific dipole in this medium. And the susceptibility of this dipole would be characterized by the corresponding hyperpolarizability, which is a nonlinear susceptibility per one dipole. So this dipole has a hyperpolarizability of the second order, gamma 2. And it interacts with two fundamental frequency photons, and these two photons induce a doubled frequency component in its oscillation spectrum, but instead of emitting a doubled frequency photon, it interacts with the neighboring dipole by means of dipole-dipole interaction, and with the assistance of an additional fundamental photon, it induces a tripled frequency component in the spectrum of dipole moment oscillation in this neighboring emitter. And this ends up emitting a tripled frequency photon. So the way it comes out of math, like I will be able to explain a bit later, it does involve cascading, but this cascading is of different nature. It does not involve propagation and separate phase matching condition. The phase matching condition would apply the same as for the direct process. But at the same time, it is a cascaded process. It's not a direct process. So this was quite fascinating. First of all, from the fundamental point of view, I got really, really excited here. Because it appears that I've done it actually in Chi5 in centrosymmetric medium, like I will be able to explain later. And we did not know about it. It has been briefly mentioned and in a couple of publications, quite much earlier publications, in Chi2 contributing to Chi3, meaning gamma atomic 2 contributing to Chi3, so hyperpolarizability contributing to the susceptibility. So, but it is not well known, and many people in the community were speculating about higher order nonlinearities existing in the medium and accounting for the local field effects in a much more simplified fashion, ignoring this cascaded effect, which could be significant. We published the papers performing it in Chi5, and that's how it was. Historically, we first did the work, and then we found out that it was already done in Chi3 domain. But the community knows very little about it. So as a result, this effect is not well studied, and it would be interesting to explore it in more depth, in more detail, as well as experimentally. So practical implications. Cascaded effects are typically stronger than the direct effects because they rely on lower order nonlinearity. For that reason, it would be interesting to study it. Also, conventional cascading in the macroscopic sense that requires propagation is not always available in some samples, in some very thin samples, for example, and is not always useful for some applications. So as a result, it all dictates that there is definitely an interest in studying this effect. So now about the theory that I performed, and it was done for the centrosymmetric medium. And I've been working on the expressions for Chi1, Chi3, and Chi5. First in the collection of two-level atoms, but later finding a different approach, which was reported in Bloombergen's papers, in order to physically understand it, because the cumbersome expressions that I obtained from the model of the two-level atoms was not very intuitive. We could not understand the physical nature of it. So doing a different way, I arrived at more elegant expressions. For Chi1, there is nothing peculiar about it, because it is proportional to the atomic density and linear polarizability of the medium multiplied by the local field correction factor. That's, many people know it. There is nothing peculiar about Chi3 being the lowest order nonlinearity in the centrosymmetric medium. Here we have Chi3 scaling as the atomic density and proportional to the third order hyperpolarizability, which is Chi3 per 1 dipole in the medium, and absolute value of L squared times L squared. That's all normal. And finally, Chi5. What we expected is really just this top term here. But what we ended up with, a couple of more terms. And these two additional terms that we did not expect initially, they scale as n squared, as the atomic density squared, and depend on the hyperpolarizability of the third order, which is lower order nonlinearity, contributing to the higher order nonlinearity squared. So this is in centrosymmetric medium when we don't have Chi2 effects. That looks like this. So, and later we came up with physical explanation, like what I shown at the beginning of the presentation, where neighboring dipoles just share their dipole moment oscillations by means of dipole-dipole interaction with each other. And this way we have higher order nonlinearity arising from a cascaded lower order effect happening at the very local scale. So, as I explained, the first term is the direct contribution, and the two additional terms are cascaded contributions of the lower order nonlinearity to the higher order nonlinearity. How do we go about studying it experimentally? That was the next challenge that Dr. Boyd raised for me. So, well, very good, but now let's figure it out. What's going on? Let's try to observe it experimentally. So there is one obvious thing about these two contributions, the direct contribution to Chi5 and cascaded contribution to Chi5, is the direct scales as the atomic density, while the cascaded contributions scale as the atomic density squared. Obviously, we need to change concentration of something and measure the different orders of nonlinearity, measure different orders of nonlinear susceptibility in the species, in the samples, in order to see some trend. And that's what I've done to experimentally separate the contributions we need to vary the atomic density. And I choose a system to work with being carbon disulfide, disgusting fluid, to be honest with you. It smells horribly. And fullerene C60. Diluted in carbon disulfide. It dilutes very nicely. They have nonlinearities of opposite signs, and they both highly nonlinear. And it was quite easy to work with, relatively easy to work with. So what I should digress here. At a certain point, when I was running this experiment and at the final stage when I was collecting data, there was a period of time when I literally lived in the lab for a couple of weeks. I only came back home to take a couple of hours of nap and to eat something quickly and to take a shower, and then went back to the lab. At night, in the morning, during the day, I was always there collecting this data. I was so excited. So, and finally, I was very happy to observe the difference in the dependencies for Chi3 and Chi5 on the molecular concentration of C60 in CS2. So I'm meeting all the details of complicated analysis that I had to perform in order to be able to estimate the value of the cascaded contribution, but it turned out that there are conditions when this contribution can outperform its macroscopic counterpart and its direct brother as well. So it was, for me as a student, it was quite fascinating, and I still have that emotional bias towards this project. And to tell you more, this project has successful continuation and is presently one of the active research directions in my group, but this is not the point. Today, I only wanted to talk from the perspective of a graduate student of Dr. Boyd. And by the way, my Monday talk at Max Planck Symposium will have relevant contributions from current time, but today I would like to stop here the research part. And what I want to add is any student in Dr. Boyd's group, here is my PhD defense, and after the defense we had a small party with my committee members. Miguel is here, and Dr. Boyd, and Professor Stroud, and I also had Louis Rosberg from physics, who was unable to stay because of other commitments. So any student in Dr. Boyd's group got multiple projects, and these projects were not quite related to each other. To be honest, some students might have been concerned, I don't know. But for my personality, it was amazing. I was really excited to give it a try in different subfields of optics. I was very much...
Things have not changed, they're like...
Yes. Yes, I'm getting there. Exactly. I'm very much excited about the fact that I was able to explore so many subfields of optics being Bob's student. It worked out perfectly well for my personality because I like a little bit of everything, and the way I arrange my research group nowadays, I have 3-5 semiconductors. I have well, cascaded effects, but now more in plasmonic metasurfaces. I also have terahertz optics together with Dr. Boyd, and I also starting new research direction with advanced materials for powerful lasers partnership that was initiated in the United States. So I have that new collaboration, and it's going to be unrelated to what I already have. So as you see, Professor Alan Wilner was very much right about Bob being infectious in the way he inspires students with his enthusiasm and his motivation. That's very true. So one tradition that I would like to mention that existed in Bob's group back then is we prepared defense posters for each other as a surprise. So the student who is to be holding his defense shows up in the morning just to find that the Institute of Optics has every door covered with its poster. And the poster, of course, he never seen in his life. So it kind of raises your spirits before the defense, which is a long and yes, and a process that requires a lot of concentration and a lot of energy, so it really raises your spirit. I was very proud about the posters that I prepared for Giovanni Pireda. That was very much in line with Giovanni's personal qualities, and by the way, he sends his regards. He was trying but was unable to be here. So it's Don Giovanni Pireda, Institute of Optics Opera presents, and the title of his thesis, conducted by Robert Boyd, sung in Italian with English subtitles. So I was very proud. Before an even better poster came out for me, prepared by Andreas Lapis, but unfortunately I lost it in my archives. I could not find it. I had a paper version at some point, and I was supposed to place it here. The poster was called James Boyd. Wonderful, please share with me. I should have asked. The poster is called James Boyd, and it is related to the subject of the movies James Bond. So I was standing there with a gun, and Bob was escaping from a fire explosion of my Nd:YAG nanoparticles. That was totally, I loved it, I loved it. It was a masterpiece. Okay, at the end, my thesis, what it was back then. I had composite optical materials. By the way, these are my Nd:YAG nanoparticles on the right-hand side. I had microscopic cascading effect that I'm so proud of. I had cholesteric liquid crystal laser. I had artificial chiral structures. What do I do with all this? And then I say, screw it, let's do it. And I defended it with the title, Local Field Effects and Nanostructuring for Controlling Optical Properties of Photonic Materials. That's how I put it under this umbrella. And no matter what I do, I derive my inspiration from Professor Boyd. In conclusion, Bob, let me just give you a hug. Okay, questions? Please. I'm sorry, could you please repeat your question? I'm a little bit.
Question is, again, in this particular moment, if I add another knob to turn, which can control the strength of dipole-dipole interaction, where would it go in the cascading step?
Where it will enter the expression, you mean? One way to control it is, here it was done for bulk materials, maybe for some composite materials, like we controlled it with changing the concentration of C60 and CS2. In terms of additional knobs, I don't have an immediate answer. I may have in 5 minutes after my talk, but it always happens like this. But what I can say is with metamolecules, plasmonic metamolecules, we have a lot of degrees of freedom, a lot of ways of controlling this. The only evil part is losses, of course, but we are still quite optimistic. So artificial structures. Controlling hyperpolarizability, that you cannot change in natural molecules, but you can in artificial structures. So that's what we are doing now, working on this.
So I have a question.
It's a great question that Zahir asked. I also forget the answer. But my recollection is that it's buried in gamma 3, and that remarkably it just falls out. That, of course, dipole, I mean, it's a fundamental law how dipoles couple with other dipoles. We did it correctly. It's in PRL, it has to be correct. But remarkably, that dipole-dipole coupling constant does not explicitly appear, and I had not appreciated that until this moment. I will go home and look at it.
Okay, yeah, me too. Okay, thank you very much. We should probably move on. Yes? Yes,
So it's Jeffrey Mackey. I worked with Bob on local field effects years ago.
Nice meeting you.
So the factor L, did any of your work verify that L is correct?
Yes, that's a separate study that I've been performing partly. So what we arrived at is conclusion satisfactory just to some degree. Some media tend to obey Lorentz model, some other media tend to obey Ansager relationship for the factor L. Like open cavity, like virtual cavity model and real cavity model in electrodynamics, in electrostatics. So what we concluded is for composite materials, for example, where we have inclusions of one type of materials in the background of other type of materials, it's more a real cavity model. And for example, for the situations where some background host is just doped with rare earth ions, that's just one example. It's more virtual cavity model. When the background is uniform, there is no composite phases in it, and it's just the doping that is present. In that case, we are dealing with a virtual cavity model. So we have a separate paper on it. We can talk.